Good evening, sir.
Good evening.
Good evening, sir.
Newton's laws of motion. Physics starts here. Until now, we developed the tools required for this lesson. When I said physics starts here, there are two things. One is, until now, we've been doing a lot of kinematics. Kinematics is basically experimental. Galileo, Kepler, René Descartes, people like these great persons laid the foundations of kinematics. But they could not formulate an idea called force. So without that word force and without a proper definition for mass, it cannot be termed completely physics. Right? Force explains many things. So until Newton came into picture, defined mass, momentum, and then force, the situation was not clear. And another thing is, Newton is a person who started a method called a scientific method in learning nature, in studying nature. Here, the scientific method means express nature in mathematical terms. Until then, the ideas of space, time were somewhat understood in a practical way, of course, not in a philosophical way. Even today, we don't have full understanding space, time, energy in the real sense. But they are so much into our use that we think we know them and we manage with them. So to that extent, people had enough understanding of space, that is this empty one from here to there, that idea was there. They could measure it with some ruler, some scale, some rope. So that idea, and time also, people had some practical knowledge. So from there, they defined quantities called velocity, average velocity, acceleration, all these things, speed. But the scheme did not get completed without these two definitions of mass and mass, momentum, and force. Three definitions rather. Newton was the first person to do this. There's a book by Newton, that is, in simply people call it Principia. The full name is Mathematical Principles of Natural Philosophy. In that book, Newton laid the foundations for what we call as physics today. So that's what I mean by saying that physics starts here. Tell me, children, somebody was saying something. And also, in kinematics, a lot of mathematics we learned, the tools. Here, the tools are already there. So we think more of the physics part of it, the feeling part of it. So that's where the lesson becomes actually interesting. Okay. So I've spoken so much. Sriya, can you summarize what all I spoke? Were you listening?
Sir, in the very beginning, many great scientists like Kepler, Galileo, and René Descartes, they were all able to start an idea with the help of kinematics and lay a basic foundation kind of thing. But
Yeah.
however, this was all purely mathematical. No one really explained it in how it occurs in nature in physical terms, like force, like that.
Okay.
So the first person,
Actually, not only mathematical terms, they used mathematics, but they were talking in terms of just experiments, but they were not able to explain why and how things happen.
yes, kinematics, as you said, is purely experiment.
Hmm.
So the first person who was able to really link kinematics with the physics that happens in the world was Newton,
Hmm.
and he defined force,
Yeah.
discovered it, and he even wrote a book called Mathematical Principles.
From in there, in that book only, he laid the foundations of what we call as physics today. Okay. He, of course, used the
Yes.
knowledge which was available with him, the knowledge which he gathered from all the contemporaries and his uh, and what you call people before him, but he's the one who organized it, who is the one organized and put it in a clear structured way. Okay, so the lesson really now starts becoming interesting. In fact, one could start physics from here also and go backwards. Anyway, let me see. And this will have so many lessons in it. Lesson 1, Newton's laws of motion. Lesson 1, mass, momentum, and Newton's laws only. We'll see whether we can complete it. I'll try. Yes. Mass of an object is a product of its volume and density. The first definition you have is this. Mass of an object is the product of its volume and density. Mass equals volume into density. Straight away, we went for a formula now. Find the mass of an iron cube of side 10 centimeters. Density of iron is so much. 7870 kilogram per meter cube. Here it is written in sentence. There it is written in the formula way, but with words. Here we wrote it in algebra form. The same thing. I'm not giving exactly the words given by Newton, which is complicated English. Original, his book was completely, difficult to understand, but later people translated, people made it look simple, but even that we are ignoring. We are simply following small ideas and very, very simple English. Mass of an object is a product of its volume and density. Okay, this volume thing is what? Simply geometrical. For a cube like this, you say volume is how much? Volume is, tell me.
10 cubes.
So the
Yes,
side cubed.
side cube. Come on, now onwards you are full, I'll give you full freedom to talk anything. Because this lesson can be really explored in a big way. Side cube. Side is, or you can write in algebra form, a cubed. That is 10 in 10 centimeters into 10 centimeters into 10 thousand centimeter cube. How many meters cube this will be? What should I write here? Can you tell me? How much should I write here in this place of centimeter cube? In meter cube, if I write
10 to the power of minus 6.
10 to the power minus
6.
6 meter cube. How do you all know? 1 centimeter is what? So 1 by 100 into 1 by 100 into 1 by 100 we wrote. This is how much? 10 to the power minus 3 meter cube. So mass of this iron is, in kilograms we'll calculate this one. Volume is already there, 10 to the power minus 3 meter cube into 7870 kilogram per meter cube. This cancels. You get 7870 into 10 to the power minus 3. So how many kilograms it is?
7.87.
7.87 kilograms. So this is the first thing in Newton's laws of motion. But I'll give you freedom to talk. So we start with the definition of mass, that is density, volume into density. Tell me. Questions, please.
Questions, please.
What's happening there? So children,
Yes, sir.
of course, you should be writing, but any question you would like to ask here? Sriya?
Sir, we directly said that mass is equal to volume into density.
Yeah. We did not say. Newton told actually.
Newton said that.
Yeah.
But how did he get it to be like that?
That is the greatness of Newton. Like
Yeah.
what do you mean by that? Tell me. What do you mean by how did he get means?
I mean, sir, volume into density. Why not take what? Here it makes sense. I agree that it is 1000% correct. But why could he not say that it is volume into side of the cube or something like that? Why define it like that?
First of all, what do you mean by density? It explains you how closely the matter is packed into that. Density
Yes.
means how closely the matter is packed into it. Say, for example, in the place of this iron cube here, you got an wooden one. The matter will be less closely packed in that. At that time, actually, people did not have a full understanding of the structure of matter, all that. But remember, or in a similar, you take one cube of cotton, for example. Even with the naked eye, you can see spaces in the middle, right? Whereas here in the iron, you cannot see.
You cannot.
And in from the experiment, you know, or from even from the common sense experience, you know that definitely the cube in which the matter is closely packed should weigh more. Isn't it so?
Yes, sir.
But actually, there's a problem here. I was expecting this question. How do you define density? Volume, of course, is okay. Easily understood, isn't it so? Because here in the space, the 3D space, you will, what you call, measure by what you call as volume. To measure volumes, you've got containers like this. In this, I've got some T here. So volume of this T is so many ml, we can say. So volume is not so difficult to understand. Whether you call it volume or anything, we definitely have this concept of the 3D space being measured by certain quantity called, you multiply one length into breadth. This will give you the spread of this space, and multiply with the projection, you get the whole space, you'll think. That's okay. But how do you define density? You'll define it as mass by volume. You understand my point?
Yes, sir.
So is density first or mass first is a question generally. This is called circular reasoning. Mass equals volume in density. Agree, volume, I have got an idea. Length into breadth into height. Length into breadth will give me area. and that whole thing multiplied by this is giving me the volume, some kind of an idea I have, you'll agree. But density, when I ask, you will say once again from the same definition, say it is mass by volume. Actually, people were struggling like this, but Newton was a very practical person. Even now, the discussion of mass continues. The concept of mass is actually very, very tricky to understand. Now people say mass and energy are equivalent. But we already have all this practical knowledge. Matter in bulk. Matter in bulk, I told you, not microscopic matter. Do you follow what I mean by that?
Sir?
What, sir? I'm asking you, are you listening to me? First of all, do you follow English? Matter in bulk, I was saying, that is big objects. I don't know whether you have an idea of how if we go on dividing, you'll get atoms, electrons, protons, neutrons, all that. That is matter at a microscopic level. That we cannot see and touch and feel. But matter in bulk, we can touch and feel. That's how we said this is matter and it's got some mass. Heaviness, people thought, or inertia, people thought. Heaviness as compared to the, of course, gravity, but inertia as compared to our ability to cause it to move or to stop. So that thing which has got some shape and size and which can be felt by touch if it is in big amounts is called matter. But how do you quantify that matter? You quantify it by a number, you give it to and call it a mass. That will be simply this volume into how closely this small constituents of matter are packed. That's what the idea was. But there should be a standard for this density or mass. There should be a standard. In the beginning, they took water. Easily available, and most important thing was water. So they said, of course, they were given different units, but the way you understand now it is, they said, if I've got 1 cc of water, what do you mean by 1 cc of water? In all the 3 dimensions, if you've got 1 centimeter cube, 1 centimeter, this same thing, 1 centimeter, 1 centimeter, if you take that much of water, if you take, they said the mass of that is 1 gram, and that 1 gram per cc is what you call density, they said. So a standard, you need to start with a standard to define this thing. If somebody called that not 1 gram and 1 cc, but something else, we would have followed it. But people, of course, will be dealing with objects. Some convenience they look at, right? I couldn't have called this inch of 10 centimeters. I couldn't have called it some 1,000, not 1,000, 1 billion, some units. If I say that will be meaningless, isn't it? Though I'll manage with it. 1 billion units of length, if I say, it looks very awkward, right? So you'll choose a particular standard of this physical quantities, mass or length or whatever. The standard they choose first was what? Water. So there the mass and density are defined together. You try to understand. If I have got one, if you got 1 cc volume here, in that much of water, the molecules are all arranged like this with a certain space between them. They said this has got 1 gram mass, and this 1 gram per cc is what they call as density. Now, every other object's mass and density were compared with water and then expressed in certain terms. It's not exactly 1 gram actually, but roughly 1 gram, 0.999 something. Now people know it. Tell me now. Look, the units, everything is human beings started defining them according to their own convenience. 1 meter, we said this much distance is 1 meter. If I call it 1 kilometer, also we would have followed it, isn't it? Some name you will give and say that one, but this is very convenient. Our height is, for example, 1.75 meters. That will be simple to manage, isn't it so? Huh? The
Yes.
most we say 175 centimeters, we say, but we don't say some 175 into 10 millimeters like that we may not give. So the whole idea started with Newton's greatness is that he instead of going for a philosophical discussion of the things, he just took things from what is available there and developed a full branch called physics. So by taking a standard like this, in the beginning, what was the standard? What do you mean by standard? Something against which you can compare every other thing. Some object against whose properties we define and compare the properties of other objects with that. That's called a standard. So the standard was what? Water. And the units were what? They said, okay, 1 cc water I can consider. In that I'll say 1 gram matter is packed. Matter there is in the form of water molecules. Now, using this, people could define mass and densities of various objects. For example, use the Archimedes Principle. This is a very old one, right? By immersing objects in water, they define the densities of various objects. You know, some object which is more tightly packed was sinking, less tightly packed than what was floating. Even now, by displacement methods, you can find out the density of any object. But remember, we need to start with the density of what first. Do you follow something now? Tell me. Sriya.
Yes, sir.
Okay, let us see. We'll continue. But now the standard is different. Come on, one of you read it, please. Please read that.
Currently, the kilogram has a very simple definition. It's the mass of a hunk of platinum iridium alloy that's been housed at the International Bureau of Weights and Measures in Sèvres, France since 1889.
Yeah.
It's called the International Prototype Kilogram, also known as Big K or LE Grand K, and it has
Lee Grand K.
or Lee Grand K, and it has many copies around the world, including 7 at NIST in Gaithersburg that are used to calibrate scales and make sure the whole world is on one system of measurement.
What do you mean by this? This NIST is National Institute of Standards and Technology, I think. This Gaithersburg is something in US only, not in Germany, in Maryland, I remember. Okay. Now, later see, water is, making water a standard is not going to work. Isn't it so? It's a liquid state. So everybody has to compare their weights with the water. Water, once again, its density, its volume changes with temperature. Density changes with temperature. Isn't it so? Tell me.
Yes, sir.
So they took platinum iridium alloy. And of course, a particular amount they took and they called it 1 kilogram. Of course, still they were following the things from the water idea only, but that much thing is the dimensions of all that is there anyway. I'm not going to the details of that, right? All that they call that kind of a platinum iridium alloy, this kind of a what you call cylinder, they call 1 kilogram. And where is it placed? International Bureau of Weights and Measures in Sèvres, that is in France. It's called the International Prototype Kilogram, IPK. Do you follow? International Prototype Kilogram, or Big K, or whatever. And it has many copies around the world, including 7 at NIST in US. Like, see, this is a person, Patrick Abbott, is a keeper of the kilogram. Look, we don't want to change the, even we don't want to touch it with anything. We don't want to contaminate it in a way. We don't want to add anything extra to it. Okay. So there are 7 copies of that in US, and many countries have got their copies. And whoever wants to calibrate their weights, they'll go to that and calibrate with that. That is the idea there. Huh? So that they used to calibrate scales and make sure whole world is on the one system of measurement. But it so happened around in 100 plus years, even this mass of this reduced by some 50 micrograms or something. 50 micrograms. You understand how accurate they want it. So later they defined, now presently 2018-19, I think it was finalized. I don't remember exact date. But now mass is defined in terms of most corrected value of Planck's constant. Planck's constant, did you hear it any time?
Yes, sir, in chemistry,
Chemistry, you write it. So they were discussing what is the, how will correct, how, to what accuracy shall we write H, they were thinking. See, even the length unit is now not the original length unit people defined. It is defined in terms of the wavelengths of a particular light. So speed of light doesn't change. Try to understand this. Constant do not change. But once you decide how much is that constant, Planck's constant, in terms of that, now people have a definition for mass, which is not yet come into the textbook because it's not easy to write one definition in terms of the Planck's constant. The current thing is what the mass definition is based on the value of, what is this? Planck's constant. So that for all people, for all times, this H will remain same and mass will remain same and mass will never change. Once you define it in terms of the Planck's constant. Tell me, children. Tell me. And this is K4, a copy of the International Product of Kilogram forged from the same platinum iridium alloy that's placed in this place called NIST, National Institute of Standards and Technology, I think, yeah. In Gaithersburg, in Maryland, somewhere in the US, I think. So like that, there are 7 copies of it there. And there'll be people maintaining it and people trying to protect it. But even that is not very accurate. Therefore, they've come to a conclusion, 2018, 2019, I don't remember exactly. All the scientists met and they agreed upon this value of Planck's constant. And from there you define mass now. How you define from that, it will take some time for you to understand. So we'll postpone it in case sometime later we'll talk about it. Are you listening, children?
Yes, sir.
See, the Newton's laws I started with mass definition. Try to understand. That's very, very important. Defining mass, defining momentum and force. At one stroke, Newton opened up what you call a complete description of nature in mathematical terms, inanimate nature, especially about the motion of bodies. Okay, I'll continue.
Yes, sir.
Then this one. What is this? Sriya, read it on the left hand side.
Yes, sir. Momentum, that is linear momentum of a body, is equal to the product of its mass and velocity. P bar is equal to mv bar. Units kg mass
Meter.
per second. Okay,
Meter.
sorry. Kg meter per second or Newton second.
Yes. Dimensional formula.
ml.
MLT minus 1. M for mass, L for length. By time. So T to the power minus 1. And it is a vector quantity.
Yes, sir.
Remember, theory of knowledge is same for everything. The greatness of Newton is that he was not having anything. Of course, he had the information from his predecessors, but he is the one who defined. Remember, anytime when you want to do something in future also, you cannot say loose words, you should define it first. So he defined a thing called linear momentum. Look, mass was not there, mass was defined. Mass is density into volume. Let's not get into the the genesis of that, which is not, maybe you don't understand it, but I just want to show you that physics is done that way. So first definition was mass. Second definition is what? Linear momentum. People wanted to quantify motion. What did I say? Motion was always attracting the human beings. Try to understand. Physics started in human beings' attempt to study motion. A subject called physics evolved when some intelligent people, whom we call them scientists now. That time there's nothing like scientist and in fact, people keep now fighting. Religious people and science people keep fighting, but in fact, many physics aspects came from religious people, for your information, because in churches the priests used to have time, and they used to have library, and they used to study. So education made, of course, this kind of a thing possible. The person who gave the Big Bang theory, the beginning, the first who proposed it was a priest, basically, because they had the access to all books, all access to the knowledge. All right. So people wanted to quantify motion. What do you mean by that? What do you mean by that? Moving motion is there, but how to measure the motion? The whole idea was basically the whole physics developed because people wanted to measure them in mathematical terms and in experimental terms, both, of course, are together. So to quantify motion, people had arguments in the beginning. They used a word called quantity of motion. What is that? Quantity of motion. The quantity of motion, first somebody said it is mv, and somebody said it is half mv square. But both are important. Now we know that using both of these quantities, what momentum and kinetic energy, one can measure the motion, one can quantify the motion, one can tell how much is the motion. So finally, people settled on momentum and called it quantity of motion. But now we don't use the word quantity of motion. Newton used it actually. We're calling it linear momentum. And here immediately I've given you one formula. A cricket ball of mass 163 grams is moving with the speed of 154 km per hour. Find its momentum. What do you do now? Mod P here I'll write. Mod P equals mass into mod V, magnitude, right? How much is this? 163 by 1000 kilograms into speed 154 into 5 by 18 meters per second, right? Tell me. Hello?
Yes, sir.
So simplify it and write. Actually, I've given you almost the real values. If somebody knows cricket, this speed is not impossible, Nowadays,
Yes, sir.
fast bowlers will go up to this speed or even more than this, but 154 is considered a very good speed. Fast bowlers do that. And the mass of a cricket ball also, you see, it is it starts from 150 something to 163 grams like this. So simplify it and tell me the units are what? Kg meter per second. All right, children. How much is this? Nearly 6.97 kg meter per second. This is what I mean by moment. And momentum is a vector quantity. To make you understand the meaning of it, I'll tell you something. There are two blocks, for example. This is moving this way, this is moving this way. Mass of the speed of this is 2 meters per second. Mass of this is 10 kilograms. And mass of this is, for example, 5 kilograms. And speed of this is 4 meters per second. Momentum of the system of masses here, for whatever reason we would like to consider them as one system. P system equals 10 into 2, 20 meters kg meters per second I cap minus 20 kg meters per second I cap. Do you follow why I wrote 5 into 4, 20? This is 0 bar. So you couldn't have told this is 10 into 2, 20 plus 20, 40 you cannot say, because this has a direction. All right? When you add up the two momenta, you'll add them like vectors. So that's what you mean by saying that it has a magnitude and a direction. That's why it's a vector quantity. In a similar way, if you think there are 3 masses like this of mass m each, going towards the center with speeds v each. If I asked you to find out the total momentum of the system, that is 3 parts taken as 1 unit, even here you will say P system is 0. Why 0? Do you know? Vectors we need so much. The angle between 3 momenta is what? 120 degrees. So even now the momentum will become 0 because some of these two will be this way and equal and opposite a third one. So momentum of the system is 0. That's what you mean by saying that momentum is a vector quantity. In other words, we cannot add momenta like we add numbers. Okay? Tell me, children. Come on, children. I'm expecting you to write. Yes, Shreya Dhama, are you there today?
Yes, sir.
Any questions? Okay, let us go in a simple way first. Bare essentials we'll talk. And as we keep doing things, of course, you'll get some more doubts. But remember, the lesson starts with the definition of mass and the definition of momentum now. Then we are ready for Newton's laws. Children, can I continue with the lesson? Can I go to the next page?
Yes, sir.
Others,
Yes, sir.
are you there, P. Vaishnavi, today?
Yes, sir. I'm there, sir.
Are you following?
Yes, sir.
And Trishul, did you join? Could you join?
Yes, sir.
Oh, from where did you join? In the bus you are or here only?
Here only, sir.
Here only. You are looking into a phone or what?
Phone.
Phone. All right. Any question, Trishul?
No, sir.
No. All right. Now I'll go for the next page, next screen. All right. The minimum thing is this, just remember the definitions and see how it is converted to numbers, all that you remember. Okay. And it's linear momentum, but somehow we are lazy. So we drop the word linear momentum until we go to rotation dynamics, where we get angular momentum. Do you follow? So until then, when we said momentum, just think that is a linear momentum. Why? Because velocity here is linear velocity. It's not angular velocity. It's not theta. It's not delta theta. It's not d theta by dt. It's not omega. Do you follow my point?
Yes, sir.
Right. Now let me continue. Newton's first law. Even this first law is not exactly the way Newton gave. Various scientists made it easier and easier for us. And here we'll write even more practical definitions for us. Trishul, read the statement. Trishul.
A body continues to be in a state of rest or uniform motion in a straight line with a constant speed unless and until a net external force starts acting
On it, spelling mistake.
on it.
So this is very popular kind of a statement we have. All right. First, let us understand the meaning of this statement. I have a table. Okay. On this table, there's a book. I'll write a book. Now, this book will be there as long as this Yogi Raghavendra comes and picks it up.
Yes.
Isn't it so?
Yes.
So, remember, a body continues to be in the state of rest. Rest, I told. The book is supposedly at rest. There's no force acting on it. Is it correct? No. The net force acting on it is zero actually. But nobody is coming and applying any force on it to move it. Okay? So the book will be there only. It is as simple as that. But how do you explain the second statement? Uniform motion people use, but uniform motion meaning is in a straight line with a constant speed. That means the body should be going straight like that without turning, and speed must be constant. That means for every second, the distance must be changing by the same amount. So how do we understand that? Shreya? How do you understand that? I'll tell you how do you understand this. Actually, I told you, I keep telling all the time, people think that natural state of a body is rest. If I said natural state of a body can be even motion, people in the beginning think, oh, is it correct? It can be rest or motion. Actually, I've not even gone to the reference frame yet. I'll keep adding statements for this statement, the same statement. But don't ever think that naturally the bodies are at rest. Remember, naturally the bodies can be even in motion, but what? Motion with no acceleration. Now look at this. I'll tell you something. Listen to me. There's a block here. Think of giving it a velocity, children. You push it like that with a velocity. So what do you expect actually? This is a surface in a lab, some tables top, for example. So it will go some distance and stops. Will it or not? On your table, you just check this, take something and just move it like, hit it like this. Giving velocity means not pushing it continuously, just hitting it like that. Do you follow? So will it stop or not?
Yes, sir, it will stop.
Stop. Why it may stop? We may think that there is some force called friction. An opposing force might develop like that, and that's why the block is stopping, we think. Now, let me say we reduce the friction and gave same velocity for the body. It's a thought experiment. Do you understand? You're not actually doing it, but thinking of doing this experiment. Now, think of reducing friction. What will happen now? The body might go a little more distance and stop. Is it okay?
Yes, sir.
Yes,
Now,
sir.
think this surface is as long as you want it, in length. Now, think of reducing friction further. This may be F2. F2 is less than F1. Now, give same velocity for the body again. Reduce the friction further. What will happen, children? It will stop somewhere here. What am I leading you to, children? Can you tell me?
Sir, after a certain point, we will reduce, the friction will be very, very small and negligible.
Let me say friction is 0. Huh?
Yes, sir.
So if I give the same velocity, what will happen? The body will never stop. And as it is moving like that in a straight line, the net force is 0. Probably there may be forces like weight may be acting, some N may be acting from the surface, but the net force is still 0. So the body will continue forever like that. In the interstellar space somewhere, there may be a small massive object which may be simply drifting in space like that. The effect of gravity and that may be not there at all. But of course, we don't know who gave the initial condition there. Here we know the initial condition. I provide one because for me, when I stand in the lab, I think I'm at rest only, isn't it? So I give a velocity there, provide initial condition and leave it. Says somebody did not see this event of giving velocity to the block. So somebody standing here, he started looking at the block from here, for example. For him, what will happen? The body continues to move forever because there's no net force acting. So this is the meaning of these two statements, children. And the body turns, even the speed doesn't change. Remember, there's an acceleration like this, which means there's a force like this. You know, when a body turns like this, where is the acceleration, children? This way. I told you already, acceleration is all the time towards the inside of the plane curve like this. You understand my point? If a body is moving like that, every time the acceleration direction is changing. Even though the speed may be constant, since the direction is changing all the time, there must be a net force acting. So if the net force acting in a body is 0, it can be either at rest like this, or it can be moving with a constant speed in a straight line without unhindered, unless until one force comes and acts on it and changes that state of motion, whether it is a rest or motion, of course. Tell me now. I want you to speak. Children, come on. Why don't you speak? Aryan?
Sir.
Aryan?
Yes, sir.
So, of course, we need to make few corrections in this statement because we're not mentioned any reference frame here, isn't it? Huh?
Yes, sir.
I'll come back to that. See, saying that table is at rest, book is at rest is correct with respect to whom?
Ground frame.
Ground frame. And ground frame is thought to be inertial frame. What is it? Inertial frame. That is, we'll think that there's no force acting on the earth and talk about it. Why? Tell me. We talked so much. Now I want the feedback from you. Anyway, finish it. I'll come back to that. Let me not trouble you by putting too much at the same time. We'll see. So a body continues to be in a state of rest or uniform motion. Uniform motion is what? Here, a motion in a straight line without bending, without turning, and with constant speed. Speed should be same means what? For every 1 second, it should cover 10 meters, for example. So next 1 second also 10 meters, next 1 second also 10 meters, next 1 second also 10 meters. And not only that, in 1/10 of a second, it should cover 1/10 of a meter. In 1/100th of a second, it should cover 1/100th of a meter. Like that, however small you make it, means finally, what should I say? ds by dt should remain constant and it should not turn. So it will be going on like that forever. It will be going on like that forever. But here I'll add something. It is very interesting. Listen to me, don't panic. Now I have a block, children. Did you write it, children?
Yes, sir.
Now, somebody tell me. I have a block like this. I'll apply net force on this for a very, very long time. I'll go on applying that force for a very, 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 very long time. And I can keep on moving on the surface like the surface is up to infinity. Tell me what is going to happen. Hello, tell me, speak. Trishul? Aryan? I'll
Yes,
go on
sir.
applying
The
the
body
force. I'll go on applying the force continuously. I think you people learning this foundation thing, all that in the lower class probably made you lose that child's regular, general inquisitive conceptual framework. Okay.
Sir, it will be the same.
What do you mean will be the same?
Sir, because it.
What do you mean will be the same? I did not catch.
As the previous case, sir.
The speed goes on increasing, right? Speed goes on increasing because force will keep accelerating it, right?
Yes, sir.
So
Yes, sir.
even if it started from rest, its speed goes on
Increasing.
increasing. How long will it increase, children? Huh?
Until we stop.
How long?
Infinite.
No.
Until we stop.
Sudesh, will stop. Why will it stop? Speed is going on increasing means why will it stop? Huh? Look, there is a speed limit in the nature. On the road, there'll be a board here that is C. What is that C? I just deliberately, this doesn't come under Newton's dynamics. Try to understand. This comes under Einstein's theory. There's a speed limit. Don't you see speed limits on the roads?
Yes, sir.
You are
Yes,
issued a
sir.
ticket. If you cross it on the highway, there'll be what you call that. They will record if you cross the speed limit. Even that's based on physics principle. Try to understand. So like that, the nature had put a limit on the speed of any object. That is 3 × 10⁸ meters per second. Only light can reach that speed, and not any matter particle. If you increase the speed, you'll give kinetic energy to the body. The energy of the body keeps increasing. So if you go on continuously giving continuously keep applying force and give speeds to the body, its kinetic energy goes on increasing. But as you approach the speed of light like this, the speed stops increasing. The mass keeps increasing. What did I say? Because no body, no particle in the universe anywhere can never reach the speed of light. Or instead of saying speed of light, there is an ultimate speed in the nature, that is 3 × 10⁸ meters per second. Only light can go with that speed, and no body, however much you go on pushing it, you do not push like this. Nowadays, you got particle accelerators. Do you follow? What is it? Particle accelerators in the labs. Electrons, protons can be made to go round like that in the accelerators, or go long distance in the accelerators where the speeds go on increasing, but somewhere they will say, come on, as you approach the speed of light, of course, they'll say, come on, we cannot run anymore. They become inert. The inertia increases. Inertia means mass in a way. So I just deliberately went a little ahead of this lesson anyway. That's not Newtonian dynamics. According to Newtonian dynamics, it is possible to get any velocity for the body. It's not really possible practically. Say something, children. You are in the 21st century. You are 21st century kids. Most of you, all of you, isn't it? All of you have born after 2000, right?
Yes, sir.
So
Yes.
you are really 21st century kids. Come on. So how do you like this idea?
Sir, why this happens?
Sudesh?
Why this happens, sir?
Why this happens? We don't have answers for why. We have not seen anything experimentally which ever went with the speed of light. Sudesh, there is so much technology right now, isn't it?
Yes, sir.
Nowhere in any experiment, people could find an experiment where they could push anything with the speed of light. We'll see. You'll know more about it later. Children, all right. For today, we'll stop, but read one book and come. This goes on, this lesson continues. Lesson 1, I put, but lesson 1 continues. I'll call it lesson 2, Newton's laws. So here, your, what you call, I can judge you people in terms of whether you are science students or not, whether you're physics students or not, math students or not, depending on your response in this lesson. The most important lesson for the for all of your what you call learning, education later. Probably it may go until 10 more years. 2 years now, 4 years in undergraduation, 2 years, for example, post-graduation, 2 plus 4, 6 plus 2, 8 plus 4 or 5 more years of PhD, for example. So until 13 more, 14 more years, for all that thing, this lesson is going to be the beginning. You'll recall my words later. Okay, right now I'll stop because a lot of discussion has to be done. We'll see. I'll end the show for now and we'll meet again tomorrow at 7:30 and be on time. Some people are joining late. Don't do that.
Thank you, sir.
I'm not
you,
I've
sir.
got closed it.